Hello everyone, this is our ECE 4960 project overview. This is our DIY drone kit. My name is Chase and I'm here with Grace, Josh, Langston, and Kyle. Our objective and motivation for this project was to design and build a fully functional drone capable of stable and controlled flight using custom hardware and software integration. We also wanted to design a drone kit that would contain all the components needed to build a drone aside from the 3D print. Another objective was to educate aspiring engineers about drone building and control while staying budget conscious.
Our final deliverables were an Android application used to fly the drone in desired patterns for at least 5 instructions, publish a companion GitHub containing the code from our design as well as other documentation, design the packaging and instruction pamphlet, as well as showcase the complete custom flight controller.
All right, so here you can see the final design of our project implementation with the Pi 4 as the brain of the whole operation.
The chassis was designed using Fusion with the goal of lightweight and easy to print. The print was done using PLA, which is a cheap and readily available plastic filament. It is sturdy enough to withstand the forces of the drone flying as well as the forces of unscheduled contact with the ground. The CAD model was instrumental in planning the placement of the hardware for McMaster Carr, which enabled us to have a place for the subsystems and wiring as well as a cradle for the lithium-ion battery. As you can see from the middle of this slide, our power distribution board is the heart of the slide. From there, each brushless motor is interfaced with the power distribution board via an electronic speed controller. The power distribution board gets its power from a lithium-ion battery, and the Raspberry Pi 4 interfaces with the power distribution board via a 12 to 5 volt DC buck converter, which then allows the Raspberry Pi in turn to interface with the motion processing unit.
Software design requirements. Our project integrates multiple components to control a flight system effectively. The flight controller was built using Python, leveraging the inertial measurement unit, or IMU data, for stabilization and receiving directional movement commands from an Android app. The Android app was developed using Java and serves as a controller via Bluetooth using BlueUART. It allows the user to send movement commands such as up, down, left, right, forward, and backwards using block commands similar to the Lego Robotics. The app also allowed for control with analog sticks, matching the pitch and yaw found in common drone controllers. To manage the motor speeds, we generate precise hardware PWM signals, or pulse width modulation signals, using the PyGPIO Python library, enabling speed configuration with the flight controller. Additionally, we use NumPy and VPython to create a 3D visual model to demonstrate the real-time IMU movement. This setup ensures accurate control, stability, and interactive visualization of the system in action.
This slide showcases the graphical user interface for our custom Android app, Build-A-Drone. This app is designed to guide users through building and controlling a drone, emphasizing both fun and educational aspects. The first screen that appears is the splash screen. The next screen is the main screen, which welcomes the user by allowing 3 options. The first option is the instructions block. This takes you to our comprehensive GitHub repository. The next button you will see on the main screen is the block coding screen option. This screen allows users to create a sequence of commands for the drone using simple blocks. Once a Bluetooth connection is established to the drone's hardware, a download button appears, enabling the users to send their coded instructions directly to the drone for execution. This feature aims to bridge programming concepts with real-world applications. The final option on the main screen is the flight controller screen. This allows direct access to manual flight control for more advanced users. The analog controls continuously send live data to the drone over Bluetooth Low Energy, ensuring smooth and responsive movements. The Android acts as a client to the Raspberry Pi server. The Raspberry Pi has a BLE server set up on it, configured using BlueArt and GATT tool protocols. The server defines a GATT profile, organizing services and characteristics to handle the drone commands from the Android. The BLE communication is structured into services and characteristics. The block coding sends a batch of commands sequentially over Bluetooth Low Energy to the Raspberry Pi. The analog flight controller continuously streams pitch and yaw values to their respective characteristics, enabling real-time adjustments. These characteristic IDs get sent to the Raspberry Pi and handled in the flight controller code. Universally unique identifiers ensure each characteristic is uniquely identifiable across devices. Bluetooth GATT allows the Android to communicate with the Raspberry Pi Bluetooth server efficiently and with minimal delay time.
So for the project overview flowchart, we begin by designing and 3D printing the chassis of the drone to ensure that it meets weight and structural requirements. Next, we assemble the physical components, including motors, sensors, and other hardware. After assembly, we install and calibrate the sensors and motors. This ensures the hardware provides accurate data and functions correctly. We test the motors by sending signals to ensure they respond as expected. If the motors are not spinning at the same speed, we revisit the calibration process to address any inconsistencies. Once corrected, we move forward. After confirming the motor's operations, we rewrite and create the flight controller software on the Raspberry Pi 4. This software integrates sensor data and motor controller for stability. We also establish communication with the controller, which is crucial for remote operation. The flight controller software, complete with PID stabilization, is uploaded to the Raspberry Pi 4. This ensures the drone can maintain balance during flight. We test the integration of hardware and software to ensure they respond correctly. If any issues arise, we debug and make adjustments. Once the integration is confirmed, we command the drone to take off. At this point, we observe its stability and responsiveness. If drifter instability is detected, we adjust the PID controllers or flight control code as needed. If stable, we proceed to test the controlled responses for directional movement. We verify that the drone can respond correctly to the commands for up, down, left, and right movement. Next, we create a Bluetooth server on the Raspberry Pi that allows remote control via compatible Android phone. The Bluetooth remote sends commands to the Raspberry Pi, enabling stable flight. If the command remote does not work as expected, we debug the communication or flight control logic. Once stable, we proceed. Finally, we design and print the packaging to create a finished product, ensuring it is user-friendly and aesthetically pleasing. At this point, the drone is ready for deployment and operation. So for the IMU code, the IMU stands for the Inertial Measurement Unit. The purpose of this code is responsible for interfacing with the MPU, otherwise known as the Motion Processing Unit, 6050, which combines an accelerometer and a gyroscope. It provides critical real-time data to stabilize the drone during flight. For initialization, the MPU 6050 IMU is set up using the Inter-Integrated Circuit, also known as I2C communication protocol. We configure its power management register to start collecting sensor data. The calibration section, before using the sensor data, we calibrate the IMU to account for drift and environmental factors. This involves averaging multiple sensor readings to calculate offsets for both the accelerometer and gyroscope. And for the data processing, once calibrated, the IMU provides raw data for acceleration and rotation. This code converts these raw values into meaningful values like degrees per second for the gyroscope and g-forces for the accelerometer.
Flight controller PCB design. To further understand what goes into a flight controller, our group designed a companion PCB. This was our group's first time designing a complex PCB, and we used KiCad to do all our design work on. The motion processing unit on this board is a BNO055, which is 3 sensors and 1 device, including a gyroscope, an accelerometer, and a full performance geomagnetic sensor. This board utilizes an STM32 microcontroller to take in data from the MPU, as well as input from an off-the-shelf RC controller such as a FlySky through UART. The motor controller outputs for the propellers are generated via 4 hardware PWM signals. The PCB can be powered through USB or through the discrete headers through UART.
During testing, the Raspberry Pi 4, which served as our flight controller, successfully set up a BLE server and paired with the Android device. It received a takeoff signal and achieved liftoff, demonstrating the effectiveness of our system integration and control design. However, it crashed immediately, quickly stabilized itself, and then remained airborne for a few seconds before crashing again. This revealed areas for improvement in PID tuning, weight distribution, and overall stability with the IMU. Despite not achieving a sustained flight, this project still provided valuable insight into Android app development, PCB designing, flight controller development, PID integration and calibration, as well as 3D modeling.
During development, we encountered several challenges. A key issue was ESC burnout, often caused by PWM signal discrepancies. We also faced Bluetooth connectivity problems and faulty wiring, which disrupted communication and functionality. Motor surges added another layer of complexity, requiring careful calibration. On the software side, learning PiOS and various Raspberry Pi libraries introduced a steep learning curve. Addressing these bottlenecks required iterative testing and optimization to ensure reliable system performance.
In conclusion, we achieved several key successes in this project, including implementation of the IMU controller, PCB design, successful app integration, and overall functional drone design. Through this process, we gained valuable skills, including PCB design, 3D design and printing, proficiency in Python and GitHub, working with Raspberry Pi operating system, newly found flight control knowledge, and experience with iterative design and testing processes.
We'd like to thank Dr. Hassan Raza for his guidance, encouragement, and time throughout the duration of our project. We would also like to extend our gratification to the Clemson University Electrical and Computer Engineering Department.